APA's weekly webinar. My name is Billy Sadek, Manager, Special Projects for APA. Just a couple of housekeeping items before we get started. The webinar recording will be posted to the APA webpage later this afternoon. You'll receive a follow-up email in the next couple of days with a link to the webpage where all webinar recordings are housed, as well as a link to our upcoming webinars. We have webinars planned out through the end of 2021, and many are open for registration. Professional Continuing Education and AIA CLU credits are being offered for today's program. If you are an AIA professional requiring a certificate, please send an email to me at Billie, B-I-L-L-I-E, @appa.org, along with your AIA membership number if you've not done so in the past. All attendees are in listen-only mode. Please type your questions in the chat box and they will be answered in the order they are received. If we run out of time and we still have questions, responses will be sent directly to the person asking the question by our presenter. If you are just calling in, make sure you send an email to me at Billie, B-I-L-L-I-E, @appa.org to let me know so I can send you a certificate if you requested one. The system only recognizes you if you log in. At this time, it's my pleasure to turn this over to Simon Goodhead. Simon, take it away.
Sure. Thanks, Billy. I just thought I'd say hi, turn the camera on just for a few minutes. Hope everybody's doing well. Thanks very much for joining us. This is going to be kind of an interesting mix of some technical components, which aren't really the main point of the presentation. It's more around the philosophies, and hopefully it's of interest. I'm going to keep the camera off just to maintain my bandwidth. In Atlanta, you never know what's going to happen, but I look forward to any questions and comments that you all have, and hope you enjoy our presentation. We'll catch back up in face-to-face at the end of the presentation. Until then, I'm going to turn this off and we'll get going with the presentation. So as Billy just mentioned, this is AIA Continuing Education session. There's the AIA slide for everybody, and then the course description. So we're obviously seeing heightened construction costs. Every bid that you get in every month is probably higher than you expected it to be. And we've also then got to balance the idea of solving design problems, which is really why the majority of you would look to do any kind of major facility project or capital expense. And you will see, many of you who have done this many, many times before, and those who are just kind of getting into the flow, that there's oftentimes this conflict between design and cost. It's not every time, but it happens often enough that we need to kind of give thought to it. What we're going to look at here is how non-standard consulting methods have the ability to kind of change and adjust construction costs or where money is deployed within the project, looking to enable design. This specific presentation is going to be more geared around fire code consultant. That's my technical background, and we'll touch on how the same philosophies in theory could apply to specialty structural engineering or facade consulting and things like that. So we'll stick to the fire side just because that's what I know technically, but we'll be thinking about it more from a contracting standpoint and what the benefits of these kind of alternative approaches might be. In terms of the learning objectives, we'll essentially, what we're going to be talking about doesn't fall under a basic services contract. And so if a lot of times when you contract with your design team, you're going to have a primary design contract between the owner and architect or owner and primary design firm. And then under that design firm, you're going to have all of the sub-consultants that are going to support the overall design effort. A lot of what we're going to talk about today doesn't fall under that basic services. And so you immediately have to start asking questions that are going to give you more insight as to what could be achieved. We're going to look at some advanced fire code methods. That's just so that you've got the technical side of things. It is pretty interesting. I'm fascinated in it. And that's from the chemistry and physics, but also the psychology of fire safety and how that affects students, faculty, folks like that. We're going to go through 4 case studies just to really emphasize that takeaway. And we're going to think about what the questions could be that you could ask moving forwards that would try and get you to that best result. The thing which I probably is probably worth touching on more than anything else is the way in which you're going to realize the benefit of enhancing the analysis to achieve the specific goal is kind of the point. It's not always going to be very evident. You're going to have to find some alternative ways of thinking which aren't typical in your day-to-day design and construction of regular facilities. Each one of these case studies are totally unique, and the solutions and methods aren't taught in classes. You can't go to university, if it's a fire engineering university or whatever it may be, and suddenly learn some of these methodologies. It's the combination of experience and looking at the specific building and then having a really holistic mindset. The odd thing here is, and this is something which we've been challenged with for quite a number of years, and actually I remember the Cox Group, which is, we're a management consulting firm, we were asked to look at how a university spent funds on design and architectural and design services, and what the outcome would be as we increase and decrease that overall spending on design and the outcome related to construction costs. Now, there's obviously a sweet spot, but there is a point where if we start right now within the design community, we're seeing a staggering increase in salaries across the board at all levels. And so if salaries are increasing by, pick a number right now, 15 to 20% a year for some of these positions that are really impactful for design projects, what's that doing to the overall cost of the operation? And if the fees are not keeping pace with that, that's one problem. But if they're tied to construction costs and construction costs are running away, we've got a whole different conversation. So we're not going to get into the nuts and bolts around that, but it starts to give you the idea of how we should be looking to achieve better value for a facility. So we're going to look at 4 examples. We're going to look at a football operations facility. We're going to look at a high-performance computing center and technology collaboration space. We're going to look at a very extensive renovation of a mid-century library and educational space into its current form. And we're going to look at a brand new addition around a 1920s structure, and how each of these really look to achieve the design vision that the two primary stakeholders, the owner operator and the designer, really had in mind when they first looked at this. So if we start off with the football operations, some of you are probably familiar with the university just from the orange that you saw, but there was an existing unlimited area indoor practice facility, and there was a new 2-story building. The overall addition would mean that the unlimited area aspect of the existing building would go away, and would have to treat both buildings as type 1B construction. That is 2-hour fire resistance and the 1-hour fire resistance to the roof structure. The contractor asked the question, hey, how are we going to get the fireproofing applied to the 70-foot high space? We've got to upgrade that. Or we end up having a separation between the 2 buildings. There's lots of downsides to that from the football operations facility standpoint and the coaches' requirements. And so the question got asked, is there a way to treat both buildings as type 2B, even though that they're assembly? that was a really interesting question. This particular project was HOK and Goodwin Mills Kaywood as the design firm, design team, and they were looking at it originally through the lens of, all of the regular progression of what you would expect to see from a code base standpoint. They then said, hey, what is it that it would take to try and get this to be type 2B, an unprotected steel for the existing building and unprotected for the two-story addition? And it was a really interesting question because it's not related to fire. When we start talking about height and area, it's realistically the people who are within the building getting out and the fire department needing to get in. And so what we really needed to do was think about it from the people who are unfamiliar with the building, those occupants who might be visiting or there for a large scale event within the practice facility. How long does it take them to get out if this was a two-story addition versus a one-story addition, which theoretically could be unlimited area? And so if we look at it through that lens, we suddenly find that we need to think about the student body and the overall faculty and the sports players, the football players that would be involved within the space. And so if you go and gather that data, and if any of you have paused to watch the students move about within any of your campuses, there's some really fascinating things which pop up. I'm going to play this video, and what you'll see is there's a chap sat down on the left side. He has a black and white umbrella, and this is just as the class starts to discharge from this particular space. The chap on the left is going to hold open the left-hand blue door that you can see on your screen, and the folks on the right-hand side are going to continue to have to open and close the door on the right. And what we immediately see is the rate of occupant egress through the left-hand side being far greater than the right-hand side. I'm actually going to mute this just because we don't need to hear all the sounds, but you can see that there's essentially three parts. Every time that door closes, somebody has to stop, put their hand on the door, open it, and then move forwards. The nice kind chap on the left holds the door open, puts his foot in front, and the flow rate through the left-hand side ends up being much higher. And so we start to see how much of a challenge a door in the path of egress can be just from a flow rate perspective. It suddenly becomes something we need to think about. What about the fire department operations? All of those things start to become important. So some fundamentals. This scope wasn't part, the scope of trying to understand, can we take this to type 2B construction, was not part of basic services. It definitely would help the overall cost of construction, but there is an increase in design cost to try and get to that point. In this analysis, one would expect there to be a fire model, but there wasn't, because this was a human behavior question, not a fire behavior question. We've got to start thinking about how long it takes to initiate the alarm, how long it takes people to leave the facility. Can we collect the correct data? It turns out, without collecting the calibrated data from that specific university, the results would have been wrong by 62%. And you've got to think about that from a time perspective. 62% error on a 5-minute evacuation time is actually 8 minutes, and on 10 minutes, it jumps all the way to 16 minutes. So from a fire safety perspective, if you weren't putting in that additional effort to collect the calibrated data, you could have a very inaccurate answer. And that's something which needed to be considered. So what was the overall outcome, though, for the owner? Two things. One, the team was able to demonstrate that type 2B construction would have been adequate based on providing detection within the building. They demonstrated numerically the comparison to the type 1B building that would have been, the type 2B building that would have been a single story. And they were able to remove the fireproofing to that structure. The other thing, which is a side effect, they managed to maintain the openness between the existing facility and the new facility. Overall, that ended up with $1 million of net savings to the university. The state approved the approach after understanding the overall comparative approach to the fire safety. And my understanding from Paul at the university is there was a very happy football coach because that space could be open to each other. I'm keeping an eye on if any questions come through. The next is a brand new high-rise office building that was really there as part of the local university in Atlanta as part of their overall approach to creating a collaboration space for technology and students and faculty. This is the Georgia Tech Coda building that Portman Architects designed. Several interesting things around this. The user, the Georgia Tech user, had defined the criteria with the focus on collaboration. My understanding, if I recall correctly, this was a trust-based project, Georgia Tech Trust, but it was through a private developer that developed the site. There is also a data center on the same site and an existing historic structure. And all three of those are interconnected through a common space down through the site. But then within the high-rise building, there's an atrium. Actually, it's a 17-story atrium made up of 3-story atriums all the way up through the space. And we'll take a look at that in a second. But the design realization was critical for the project to succeed. There had to be the ability to create these collaboration events and collisions between the students and private industry. So the questions which had to be answered was, how do we get 17-story atrium made up of multiple 3-story atriums to work? How do we get a 5-story facade staircase halfway up the building? How do we get a 5-story deep parking structure to work? And how can we store 72 hours of diesel in a city center site safely? So there's a lot of different moving parts and pieces here. Some things that need to be considered. Here you can see the streetscape between through the center of the site, and within the middle there you can see the atrium sitting on top of a single column. To the left you can see the historic building and the data center, and to the right you can start to see the types of collaboration spaces within the building. How's the space going to be used, and what type of vehicles are going to be present? When we step back and think about it from a design perspective, this has a lot of different challenges. And so what you'll find is when you start stepping outside of basic services into these more advanced kind of analyses, you find the answers in the most obscure places. The most bizarre answer for this one actually came about 2 o'clock in the morning. This was a personal experience of mine where I was making a milk bottle for our baby twins. So 2 bottles every, within the middle of the night. And at 2 a.m., watching this baby Brezza create the bottle of milk, I realized that this was the Coda atrium upside down. And what we were looking to do was entrain the smoke to dilute it and try and create this atrium space. Within the basement, there's a lot of questions going on around the overall mechanical ventilation requirement because it's a basement parking deck. But here in Georgia, we also applied the life safety code, so it needed some smoke control system because it was so deep. Can the two come together and actually create efficiencies? So when we look at the collaboration core, you can see how the spiral staircase really lends itself well to a movement around the perimeter of the space. We've got this glaze component, and as we start to think about how that smoke could move, we can move around the glass facades through a single point on the side inlet and exhaust to a single side and create an incredibly efficient smoke control system that keeps the smoke within the 3-story space. And so rather than dealing with a 17-story atrium, we're actually dealing with a 3-story atrium stacked on top of another 3 stories and stacked on top of another 3 stories. Looking at it from a holistic standpoint also meant, and you can see here past the pool table, that the elevator lobbies, which are required here in Georgia, went away. That meant fire doors, smoke doors. We also managed to think about how to decrease the overall exhaust rate. And so it became a very, very efficient system. And it achieves that primary objective of having that collaboration core open. The very deep basement also required a smoke control system because it's here in Georgia. And in actual fact, by overlaying the mechanical system requirements for carbon monoxide and nitrogen dioxide and looking at it through a truly collaborative basis, the smoke control system ended up being able to provide a much more efficient mechanical exhaust system for the carbon monoxide and nitrogen dioxide. And that meant several things happened. We could remove one of the firefighting stairs because we could demonstrate the level of safety in the basement. We removed a staircase to be able to show, because we could increase the travel distance, and also made the exhaust shafts more efficient for the mechanical system, with a total savings somewhere, well, we'll come to that in a second, but we can see that the jet fans here running, just all they're doing is redirecting smoke and moving them through the space in a very purposeful, very direct manner, rather than just arbitrarily moving air across the entire body. It's a very directed approach. Added to that, sorry about the picture here, but added to that, we've also got the 72 hours of diesel sat there within the basement. Let's see if we can move that over for you. You can see here that each of those doors holds behind it 3,000 gallons of fuel. There's then special piping through to those spaces, and then additional separation from unit to unit. That was a very important piece of the puzzle to make the data center able to work from a backup power standpoint. The big things with this was the authorities having jurisdiction. It took multiple meetings and it took coordination between city, state, the owner, the developer, and also the design firms. And it was by being involved early, and the trust and communication ensured that there was never any gotchas. The AHJ for this project was incredibly proactive in ensuring they reviewed and understood some of the very technical aspects that, quite honestly, haven't really been used in the US very much at all. Overall, the understanding is that there's about $3 million savings for the parking deck and probably about $500,000 of savings for the atrium. Those two things, again, would not have typically been seen or been possible by following just a basic services type contract. This is a bit different because it brings in that private developer into what would otherwise be a university-led project. But the university was really driving the need for the development through their foundation. Let's take a look at extensive renovation. This is BNIM and Praxis 3 for the Crossland Tower and Georgia Tech Library. It was a very interesting project. 1950s-ish era for the library, a little bit later for Crossland Tower. And because of the extent of the renovation, both buildings were essentially required to be treated as new from a fire safety standpoint. All of a sudden, that meant introducing pressurization systems. We've got to try and maintain the gorgeous ceramic tiles within the staircase, levels of detail that were going into maintaining handrails and window framing systems. The fire engineering side of things was very much outside of the basic services. When we would typically look at this type of building, things like, my background expertise was fire safety, that would be included as, provide a code compliant building. from the facade perspective, how are we going to achieve that quality of facade that speaks to the 1950s, but addresses the modern energy conservation needs? Each of those different components are perhaps outside of what would normally be considered. The design team can handle a lot of the analysis. The easiest one in many instances is going to be around the smoke control system. We've got so many different pieces of the puzzle moving around here, and it's really a bit of a whoa. That's a lot. So what's going to be the best value to the best value to the owner? The question essentially was, we can get you the basic services for free for the smoke control system analysis, or we can pay whatever it was, $120,000 to have the analysis done. Now, the immediate answer to that would be, I'll take the free version. In fact, I was thinking about doing a poll on this, and I got a little bit scared because you would have seen that it was a trick question. The actual cost estimate for the free version was $1.2 million more than by paying the additional effort that was outside of basic services. And so it's one of those examples where the providing that additional input could actually be a significant cost saving. And the question is essentially, what would you do in that situation, right? Have you even got the ability to make that type of decision, or does the policies and processes create too much of a challenge to overcome, and it ends up being more, it ends up being leaner to pay the additional construction cost, even if it diminishes the design? So those types of things end up being pretty difficult to try and unwrap within any institution. It's going to become possibly even more complex as we move forwards, and construction costs continue to go up, lead times continue to go up, and the scarcity of skilled labor and designers becomes more prevalent. We're anticipating that the overall shortage in the architectural and engineering industry is going to start tapping on the door of a couple of 100,000 within the next 5 to 10 years, and that's significant. And I'm not sure many firms are really geared towards it, and I'm not sure many owners really recognize the challenge that the design industry is going to be facing in terms of obtaining talent. Going back to the technical side of things, some of the questions might be, what were the actual as-built conditions? That is going to start to dictate. On the lower level of the library, there were 2 beautiful side vents from the old air conditioning system. But on the second, third, and fourth story atrium, there was actually roof-mounted opportunity. How can we integrate that smoke exhaust system? Those are things which cannot be fully digested within the hand calculation. That would be the free version. What's the dimensional limitations on inlet air? There was one calculation for this particular project that anticipated almost 100% of the facade on the backside of the building, opposite to where you see here on the right, would actually need to be openable just to provide enough relief air path for a hand calculated smoke control system. And then what does the designer actually want to achieve? BNIM and Praxis 3 were very clear about what they were looking to get to with respect to this building. And that's, I walked through this with Brian Tanner a couple of weeks ago, and he was showing me some of the fine details around this project, and it really is quite fascinating. So the overall outcome of this, we ended up somewhere around $1 million of savings. There's lots of interconnected spaces that kept the original fabric intact. When we look at the building as a whole, rather than discrete systems, it actually meant that we were able to think about how the Crossing Tower connected to the Price Gilbert Library, the different levels of the Price Gilbert Library were able to interact with each other, but also independently. There was a basement connection, which then went through to the adjacent building, which actually ends up being in several movies, the Clough Learning Commons, the design of the space was accounted for. There was sensitivity to the mid-century design aspects that could be maintained, rather than using the, in this instance, the fire codes as an instrument to achieve a level of safety, which, quite honestly, for this building, ended up far exceeding the level of safety that would have been prescribed by the code. So you end up saving money, but also increasing the levels of safety. And that's really the type of thing which, in this instance, fire engineers would aim for. But then other specialty consultants would also aim for. I think about the structural engineers for the Apple store in Chicago, and they had the Miracle Beam. The beam that runs across that store in Chicago takes the load, but it also has all of the systems and mechanical and electrical systems to operate the whole store. And so that was a structural design solution that wouldn't necessarily have been very evident if that design team had just followed the standard procedures. Yeah, Billy says, just remember, if you have questions for me, please type them in the chat box. The last kind of big example I wanted to go through was the Duke's West Campus Union Building. This was Grimshaw that provided the images. Actually, Grimshaw provided all of these images for the project. It was a beautiful 1926 building. If I remember correctly, it's the Cambridge Hall. And the heavy timber that you can see within the image on the left was going to be maintained, actually wrapped around two sides of the building. The hope was to have those two structures open to each other. There was then going to be new assembly spaces added, which you can see hanging suspended from the ceiling there, which were going to be able to provide eating spaces and study spaces. And then we've got the food service throughout that lower level, and actually in the basement is the full kitchen for a lot of the prep areas. But there was a really strong desire to keep the space open and with the high design. And so as you see in the next few images, there's a lot of very modern materials mirrored against some of the classic materials. You can see that here with the glass and the steel and the heavy timber. But then the thread of new wood coming into the building to try and maintain that language, but still tying in this glass and steel idea of the modern aspects of the building. And so one of the questions which was raised, and this is really from a design standpoint, the preference would be to keep the steel unprotected. Yes, that's got a cost reduction, but it was primarily being driven by a design preference and a design enhancement. There was a very strong desire to keep the atrium completely open to the 1920s structures. That openness was there for the overall flow and connectivity of the spaces, so it didn't close off the old from the new. There was a need for a very efficient smoke management system to reduce construction costs, but also reduce the structural load of the roof of the atrium. And of course, there was always the chefs that wanted the solid fuel burning equipment. I think the one that sticks in my mind was the wood-fired pizza oven. And I seem to remember there was a tandoori oven and a barbecue pit. So we also need to think about those things from a fire safety standpoint. One of the most obvious is, let's accept that there's that fuel in there and that could be a ignition source. Under controlled conditions, though, it's not necessarily going to contribute to a fire. So how do we maintain the balance with the design and the intended use of the building? In terms of How to approach this design, again, Grimshaw did a great job here recognizing that, a basic services from the specialty consultant wasn't going to get to where they wanted to be. And so a very holistic approach needed to be considered. Who are the users? Who's going to be in the space? That could be faculty, it could be students, it could be visitors of students. This is a pretty significant epicenter for food within the side of the campus. The question comes up, how many people will be in there? Well, we can follow the prescriptive requirements of the North Carolina Building Code, and we understand how many people there are. Except, is that how the building's going to be used? In reality, are we actually going to be dealing with more people or fewer people? What is the right number and what's the right distribution? How are the different spaces being used? And also, sounds a strange question, but how open is open? Some of these spaces probably are going to start tripping into some of the aspects around mezzanines, or maybe we need to have, from a design perspective, something completely open to the atrium space. And there's other things which we can truly enclose and move away from the atrium space because of inefficiencies in the smoke control system. You can see on the right-hand side of this image, the, I think it was 1940s portion of the building, which was a lot harder to deal with, actually, than the 1920s structure, which is in the foreground at the back of the photo there. Schedule for this project was key. The idea for many design consultants or specialty consultants, again, depends on the specialty, there's going to need to be iterations. We're looking at this is how the system would work. That doesn't work. Let's go back to this drawing board. How about this system? That actually fails in the analysis. And let's revise the iteration. That's great, but we had already, for various reasons, lost 6 months in the design schedule. Right? So schedule needed to be key, it needed to be right, and it needed to be right within the first couple of times, not in the fifth or sixth time. There was questions around, could the archaic buildings be altered, or was there really a preference to leave them absolutely alone? One of the things which I remember was very interesting in the Cambridge Hall building was the ceiling jet velocities within the heavy timber was so high, it was causing failure to some of the assembly spaces that were being suspended. How can we deal with that nuance? We don't want to close it off, but we need to change some of the output characteristics of the way, in this case, fire and smoke behaved. And then the big question for this building was, can the consultants and the authorities having jurisdiction align on the process and the technical solutions? I know I ended up, I got taken for one of the best burgers I've ever had as a result of a very good meeting. And the only part of the meeting that happened was we got alignment with the AHJ. We sat there, explained the situation, explained the condition, had an adult conversation. Were able to delve into some of the technical aspects and got agreement from the local authority that, yes, we did indeed know what we were talking about. And yes, they did agree that a safer solution was more appropriate. That sounds funny when you say it like that, but it's a real situation. There are some authorities that, in an effort to avoid making decisions, revert back to what they know. And as a result of that, we end up with design solutions that are less safe than the design being proposed. And that's something which the design teams, and again, whether that's structural, facade, elevator related, fire code related, the conversation within the design team has to take place, and it also needs to take place with the owner, and make sure that everybody's going to be aligned around something which is inherently, meets a minimum level of safety, but isn't as safe as the proposed design. The solutions for this for this particular building ended up, from my memory, being an advanced analysis and coupled fire and egress models. That means there was an egress model performed and there was a fire model performed, and the two get overlaid. That process was, back when this design was done, was actually manual. There's now automated coupling of those models. But when we think about human behavior and the relationship to fire, we can get pretty granular now, but we need to make sure, as I said in the earlier conversation, earlier case study, the egress component needs to be calibrated for the actual users. And what I mean by that is, if you go to a university building in the South, right now outside it's 95 degrees, it's about 90% humidity. I promise you, if you're on campus right now, you're moving very slowly from building to building so that you don't get too hot and sweaty. Once you're within the building, you spend a lot of time cooling down. We can take the reverse of that and say, if you're in Chicago in the winter, you may be approaching your outdoor environment a little bit differently. Those two examples, the faculty and student population on those two campuses move very differently from each other. We know that through intuition, but what you'll find is if you go and study that student population, they do move very differently, and they probably also move in slightly different group structures. And then we can apply that type of thing to the models. The fire modeling allowed the reduced exhaust rate, reduced inlet air path. I remember seeing just the most unbelievable things of people tunneling into buildings and doing vents and tunnels and inlet air paths, and that doesn't need to happen anymore with the technology available to the engineers. But it was something that was really important, and you can see the facade on the right hand side here, why that sensitivity to the facade was going to be so important. And this also took the building from type 1B construction to type 2B construction. So that dropped 2-hour fire resistance from the new structure and allowed the openness to the wood frame building. And that also kept the bridges, the glass and steel bridges, unprotected. It meant that the suspended area you see on the left-hand photo could be unprotected, and really let that steel come through and look pretty nice. Overall, this is probably this particular project had a lot of the different elements that make the fire engineering side of the world pretty interesting, but it really goes to highlight where design is a key component, and there's the ability to think through how the design team interact. There's the ability to really move the design needle forwards, but also be sensitive to reducing the overall construction cost. And that's something which I really hope would be a takeaway for many of you. I did go through those a bit quicker than I expected, and that's not a bad thing, because it gives me the opportunity to kind of really think through and come back to these points. Large populations, existing buildings, and high design. The minimums can be exceeded with good science and engineering, right? And that can also result in construction cost reductions. I think about firms like Lurch Bates with their facade consulting capabilities and elevator consulting, right? Those are two very specialty consulting disciplines that really lend themselves well to the bigger, more comprehensive thought that goes into some of these things. I think about some of the specialty structural engineers that we come across, and their ability to deal with things as diverse as cross-laminated timber, all the way through to how we deal with some light and heavyweight steel structures. The science and the engineering is only going to be achieved by compensating those specialty disciplines. And while those sit outside of basic services, they're just not going to be realized on a regular basis. Now, the basic service contracts will rarely, if ever, encourage that dynamicism of thought. And that's really pretty important, because it's the dynamicism of thought that brings the cost savings, it brings the realization of design. And so if we're also going to be seeing this constraint on the architecture and engineering disciplines over the next 5 to 10 years with respect to availability of talent, reducing fees, like, and continually to maintain fee pressure as a percentage of construction cost, you're going to find within the owner community diminishing levels of standards and loss of design capability. And it's the design capability which is really there to help deliver the solution to the problem being raised. If that's trying to drive student recruitment, if it's trying to drive revenue, if it's trying to drive turnover of classrooms. I remember I was looking at one of the Living Building Challenge projects, and one of the things which was in theory going to be quite possible was a large number of classes using the only large scale available classroom within the building. And one of the questions, which I don't think it was really ever asked in detail, but one of the questions that I would ask if I was a facilities person is, how can we increase the turnover rate of the classroom? And that means you need to start looking at people movement analysis, right? How does the flow of people work into and out of the building to maximize the use of the square footage? If you're looking to try and drive population growth within the university, but not drive the facilities footprint growth, which, you know, the pandemic might be teaching us we've got the ability to do, how do we maintain that turnover of the classroom space and layer into it the potential discipline of cleaning and cleansing those touch surfaces? I think overall, owners need to be clear with designers about the role design has within the project. I think that generally speaking, that's very clear, but it then comes with the footnote saying, and the expectation is that, you know, your fees are going to be low. And the interesting thing, just from observation is, and from personal experience, the lower we drive fees, the higher we drive construction costs. And you saw several instances over the past, 4 case studies where, just from those 4 case studies, that number is about 10 to 1. For every dollar you save on consulting fees, you cost $10 more in construction cost. Now, I don't have the data yet to demonstrate whether that scales to the lead designer level and the rest of the MEP and structural and core disciplines. What I do expect is that there is a ratio. And we need to be okay with that. We need to be okay with spending less on design and the construction costs going up, or the construction estimates being well over because of the lack of detail within the design. And the lack of detail in design isn't necessarily the result of the designers trying to scrimp and save. It's the reality that labor costs go up. If fee costs don't go up, we're not going to be spending the same amount because we still need to pay everybody's salary, or we start laying people off. There's a joke: people don't go into architecture and engineering to make money. Certainly the value proposition doesn't seem to make sense from the outside looking in. I think here partnering and being inquisitive is the key. If we're inquisitive and we ask the questions, we've got a greater ability of finding answers that we didn't necessarily expect to see. With that, I'll take any questions. I think we're just about 50 minutes in, and happy to field any questions. I've got a couple of the other APA slides. See if this works. Hello. Got a couple of the other APA slides if anybody wants to take a look through those.
Okay, Simon, we have a couple of questions for you. First one, how was the lighting concerns solved, such as task lighting, security, or exterior lighting that could tie into the fire code concept?
How was the task lighting?
How was the lighting concern solved?
Billy, it sounds like you're saying lighting.
Yes, lighting, like light bulb on and off. How was the
Okay.
lighting concern solved, such as task lighting, security, or exterior lighting that could tie into the fire code concept?
Well, I don't know much about lighting, but that would be another example of the specialty consultants, lighting consultants, of course. In many instances, the automatic assumption from a fire safety standpoint is there is no lighting, or the lighting is the minimal that you'd expect to see with the emergency lighting provisions. And that's within the building, but all the way through the exits and the exit discharge through to the public way. If it goes beyond that, that's great, but it's not necessarily something that designers can hang their hats on. And what we do within the exit signage is start looking at whether we're going to be using backlit or reflective signs, and that starts to change some of the really fine-tuning technical parameters, which are way beyond the scope of this conversation. Does that help? I don't know if that answers the individual's question.
You'll let me know. Our
Okay.
next question, what are the primary bases of the cost savings as shown on the slide? Are these based on construction costs if it weren't for performing the model?
Good question. So the football operations facility, the contractor was the one who actually made the initial call to say, hey, can you take a look and help with this? So the contractor had actually penciled in the exact number that was going to be impacted for that project. Within the high-rise building, during a design team discussion, again, the contractor said, why are you doing all these things? If we get rid of that, it'll save us. I think the saving was $300,000. And the answer, of course, is absolutely, we can do that. These are the things which we've then got to add back in. And they added that up, and it was $3 million. So we know that there was a net $2.7 million just from the one specific item that was related to the parking deck. The Crossland Tower, the BNIM Practice 3 project, that was actually a pricing exercise at the end of schematic design, where they had the contractor price an alternate bid that would have used the actual design they ended up with. And the overall alternative bid was a deduct of 1.2 million. And within the Grimshaw project, there was no real way to quantify those savings, and I don't think I did quantify them. But if you remove fireproofing from a 2 hours to zero on a $90 million-ish building, it's a pretty significant number.
Okay. As a follow-up question to that, are the main cost drivers that allow substantial savings, are they material, smoke evac systems, or what?
Again, it tends to be varied. Sometimes it's material costs. Sometimes it's a reallocation of costs. So rather than spend, $500,000 over here, we're going to spend the $500,000 over there, and it becomes a design enhancement rather than overall cost reduction for the building. Sometimes it's with creating more efficient systems. The other thing is that once we start getting into that level of efficiency, we're using, again, just using fire as an example, but the same would apply to other specialty disciplines. We're using mathematical and engineering technology that allows us to be very granular in what we're looking at achieving. If we then overlay the design aspects, we end up bringing in both the cost reduction, so using the Grimshaw building just there, we end up layering in a reduction in the smoke exhaust system, a change in efficiency in the inlet air path, removing the fireproofing to the overall structure, and creating the openness between those different spaces. Within the Portman Architects building, for the 3-story spaces, it just became a case of making the smoke exhaust system more efficient by looking at it through a different kind of geometry and science and engineering basis.
Okay, thank you. Our next question, can these parameters that you've set out, can they be used on remodeling a building as well as new construction?
Actually, yeah, it's funny you should ask that, Billy, but you'll notice that the football operations facility was an addition. The Coda was, the Portman Architects was a ground up, but the Price Gilbert Library, the BNIM in Practice 3, that was an addition, or actually that was a major renovation, and the Grimshaw project was a major renovation and addition. So I would say that in many instances, the greater value for this type of methodology actually comes from existing buildings rather than new ground up.
Okay. Well, Simon, that's the end of our questions for right now. I'd like to thank you for this fantastic presentation. I know I learned a lot today. And to our attendees, as always, thank you so much for taking time out of your extremely busy schedule, especially in this now pandemic that we're in again. So until next time, be safe, stay healthy, and have a wonderful afternoon. Goodbye now.
Thanks for having us.